The race to return to the moon is underway. Or at least, that's what it looks like. For more than half a century, the footprints left by 12 astronauts have remained undisturbed on the lunar surface, preserved in perfect stillness. They stand as a quiet reminder of a different era, when reaching the moon was as much about geopolitics as it was about exploration. The plan this time was different, not simply to visit again, but to begin something more permanent, a sustained human presence beyond Earth. And yet, reality has not unfolded quite as expected. An uncrewed test mission successfully launched in late 2022, marking an important step forward. It demonstrated that the core systems could function together in deep space. But the mission that follows, the one carrying humans, has yet to leave the ground. Delays have continued to accumulate. Launch windows have come and gone. And for now, there are still no new footprints on the moon. So the question naturally emerges, what exactly is happening? Is this simply the kind of delay we should expect from a program of such scale, or are there deeper challenges only now beginning to surface? To understand this, we need to look beneath the surface of the program itself. From the technical issues that are currently holding the next mission back, to the broader strategic decisions that are quietly reshaping the entire roadmap. Because what we are attempting here may be one of the most complex engineering efforts ever undertaken. Not just to reach another world, but to remain there. The program was first outlined in the late 2010s with the ambition of defining the next era of human space exploration. In many ways, it was seen as a continuation and perhaps an evolution of what had been achieved decades earlier. Back then, it took less than a decade to go from the first tests to human footsteps on the moon. With everything we have learned since, it would seem reasonable to assume the journey should now be easier, but the reality suggests otherwise. Years after the initial announcement, we are still not as close as many had expected. For now, the immediate focus is the next mission, the first to carry humans into the vicinity of the moon since the early 1970s. It is not designed to land. Instead, its purpose is more fundamental: to verify that the systems required for human survival, life support, navigation, communication, and safety can operate reliably in deep space. Over the course of a mission lasting around 10 days, the crew had originally been scheduled to launch in the early part of 2026. But since then, a series of technical delays has gradually pushed that timeline further and further back. What began as an early-year launch has slipped, first by weeks, then by months, which leads us to the key question: why? To answer that, we need to step through what has actually happened, piece by piece. On the 17th of January, 2026, the rocket system and its crew capsule were rolled out to the launch pad in preparation for what was expected to be an early February liftoff. At first, everything appeared to be proceeding as planned. The rollout was smooth. The systems were in place. And for a brief moment, it seemed as though the timeline might hold. But that was, in many ways, where things began to change. Roughly 2 weeks later, the first full fueling test and countdown simulation took place. This type of rehearsal is designed to mimic the final hours before launch as closely as possible. Loading the rocket with propellant and running through every critical step, it did not fail entirely, but it also did not succeed in the way it needed to. During fueling, engineers detected a leak of liquid hydrogen. On paper, this might sound like a routine issue. In practice, it is anything but. Hydrogen is the smallest molecule known, capable of escaping through the tiniest imperfections, and at the extreme temperatures required for spaceflight, around -250 degrees Celsius. Containing it becomes even more challenging. So while a leak was not entirely unexpected, it was also not something that could be ignored. This is not the kind of problem a crewed mission can simply tolerate. The issue required the replacement of seals and components within the ground support systems, a fix, but also the first clear sign that things were not as stable as hoped. A second rehearsal followed in mid-February, and this time, the results were far more encouraging. The rocket was fully fueled, with millions of liters of cryogenic propellant successfully loaded into its stages. Countdown procedures were completed without incident. No leaks were detected. And for a moment, it seemed the system had finally proven itself ready. Until, once again, it wasn't. In the aftermath of the test, during what should have been a routine procedure to clear and repressurize the system, engineers noticed something unexpected. Helium, a gas that plays a critical role inside the rocket, was not flowing as it should. Unlike hydrogen, helium is not used as fuel. Instead, it serves a quieter but essential purpose. It maintains pressure within the fuel tanks and helps clear the engine lines before ignition. Without it, the entire propulsion system becomes unreliable. A disruption in its flow is not a minor inconvenience. It is a mission-level risk. The source of the problem was eventually traced to a faulty seal and valve deep within the upper stage of the rocket. But there was a complication. The location of this component made it inaccessible while the vehicle remained on the launch pad. And so, despite all prior progress, the entire structure, standing close to 100 meters tall, had to be rolled back for repairs. At this point, the pattern was becoming difficult to ignore. These were not isolated inconveniences. They were symptoms of something more fundamental. A reminder that increased complexity does not always translate to increased reliability. Modern systems involve more components, more interfaces, and more points where failure can occur. And unlike earlier eras of spaceflight, these missions are not launched frequently enough to maintain constant operational rhythm. Decades ago, the first heavy-lift rocket of its kind flew in the late 1960s. Less than 2 years later, it carried humans all the way to the lunar surface. Today, the timeline looks very different. Less than 2 years after that first test flight, humans were already standing on the moon. The pace was relentless, almost difficult to imagine today. By comparison, the most recent launch of this current system took place in late 2022. At the time of recording, that is approaching 4 years ago. And that gap matters more than it might seem. When launches are separated by years rather than months, something subtle begins to happen. Skillsfade, procedures that once felt routine become unfamiliar. The quiet, accumulated experience that teams rely on begins to erode. It has been noted that operating a system of this complexity so infrequently can lead to exactly that kind of degradation. In simple terms, people are not getting enough repetition. And in an environment where precision is everything, a lack of repetition can lead to mistakes. There is, however, an attempt to address this. The long-term plan is to significantly increase the launch cadence, aiming for roughly 1 mission every 10 months. The idea is straightforward. More frequent launches would keep both the hardware and the teams in a constant state of readiness. But for now, that remains an objective rather than a reality. Before any new rhythm can be established, the next mission simply needs to leave the ground. And beyond the technical issues, beyond the leaks and the delays, there is a deeper consideration beginning to take shape. Risk. It has been more than half a century since humans last traveled beyond Earth's orbit toward the moon. In that time, our expectations have changed. During earlier missions, uncertainty was part of the process. The risks were understood, but they were also accepted as necessary. Today, the situation is different. We know that reaching the moon is possible, but that knowledge also brings a new standard. The tolerance for failure, especially when human lives are involved, is far lower than it once was, and the reality is difficult to ignore. Sending humans back to the moon after more than 5 decades is not simply a repeat of what was done before. It is, in many ways, a return to an environment that remains inherently dangerous. This time, the systems are new, the software is new, the teams, in many cases, are new, and the rocket itself has only flown one. That previous mission was widely considered a success. It demonstrated that the core architecture could function in deep space, but it also revealed small irregularities, subtle anomalies that, while manageable in an uncrewed test, could become far more serious with astronauts on board. And so a delicate balance emerges. On one side, there is pressure to move forward, to meet timeline, to demonstrate progress. On the other, there is the understanding that even a single critical failure could bring the entire program to a halt. That tension defines the current moment. The first mission eventually launched after multiple delays. Lifting off in late 2022, it marked the first time this new generation of spacecraft had ventured beyond Earth's immediate surrounding. The journey lasted just over 25 days, carrying the capsule on a distant path around the moon before returning safely to Earth. By most measures, it was a success. But as with many things in space exploration, the most important details only became clear after the mission was already over. As mentioned earlier, the mission was, by most measures, a success. It demonstrated that a spacecraft designed for human travel could once again reach the vicinity of the moon and return safely to Earth. That alone marked a significant milestone. In fact, some aspects of the mission performed even better than expected. The service module generated more electrical power than it needed, leaving enough margin to capture a striking perspective of the journey itself. One image, in particular, shows the spacecraft turning back toward Earth. A small, distant sphere suspended in the darkness. It is a quiet reminder of just how far it had traveled. But the full story only began to emerge after the mission had ended. During post-flight analysis, engineers started to notice details that had not been visible in real time. Subtle at first, but increasingly difficult to ignore. Among them, one issue stood out above all others: the heat shield. This component is, quite literally, the barrier between survival and destruction during re-entry. As the capsule returns to Earth, it encounters the atmosphere at speeds approaching 40,000 kilometers per hour. At those velocities, the air itself becomes a source of extreme heating, generating temperatures capable of melting most materials. To withstand this, the shield is covered in a protective layer designed to slowly burn away, carrying heat with it in a controlled process. But what was observed after the mission did not fully match expectations. Inspections revealed that this outer material had chipped and eroded in over 100 distinct locations, not in a uniform pattern, but in ways that had not been seen before. What makes this particularly notable is that a similar material had been used in earlier missions decades ago, without showing the same behavior, which raises an important question. If the material is familiar, why is it now responding differently? And more importantly, what does that mean for the missions that follow? This shield is not just another component. It is the only thing standing between human life and temperatures intense enough to destroy the entire vehicle during re-entry. And yet, fragments of it were found to have broken away. The investigation that followed revealed something both subtle and concerning. During re-entry, as the outer layer of the shield is exposed to extreme heat, gases are generated within the material itself. Under normal conditions, these gases escape gradually through the charred surface, relieving internal pressure. But in this case, that process did not work as expected. The material did not allow those gases to pass through efficiently. Instead, they became trapped beneath the surface. As pressure built up, the structure began to fracture from within, leading to the cracking and shedding that had been observed. Individually, these imperfections might seem manageable, but taken together, they point to a scenario that cannot be ignored. If the damage were to reach a certain threshold, the protective layer could fail entirely, and at that point, the consequences would be immediate and irreversible. That is not a level of risk that can be accepted when a crew is on board. In response, a decision was made that, at first glance, might seem unexpected. Rather than redesigning the shield itself, the approach to re-entry is being reconsidered. During the previous mission, the spacecraft used a technique often described as a skipping trajectory. It briefly enters the upper atmosphere, then rises back out before making a second final descent. This method helps reduce speed gradually and lowers the physical strain on the crew. However, it also extends the duration of heating, and in doing so, it appears to create the exact conditions that allow gas to accumulate within the shield material. So for the next mission, that approach will be changed. Instead of a shallow, multi-phase descent, the capsule will follow a steeper and more direct path back to Earth. This means higher forces acting on the crew for a shorter period of time. But it also reduces the opportunity for pressure to build up inside the shield. It is a trade-off. Greater physical stress in the moment, in exchange for a more predictable thermal environment and a lower structural risk. A significant adjustment, certainly. But as it turns out, not the only major change that has recently emerged. From the very beginning, the structure of the program seemed relatively clear. The first mission would demonstrate that the rocket and spacecraft could travel to the moon and return safely. The second would introduce a human crew, validating the systems required to sustain life during a journey around the moon. And the third was intended to complete the sequence, returning humans to the lunar surface. For nearly a decade, that third mission was presented as the defining moment, the point at which human footsteps would once again press into lunar soil. But as of early 2026, that plan has changed. The landing has been removed. Instead, the mission has been redefined as an extended systems test in low Earth orbit, lasting roughly 30 days. At first, this may seem like a step backward, but the reasoning behind it reveals something more nuanced. The challenge is not a single system. It is the interaction of many new systems, all operating together for the first time. To reach the surface, the crew capsule must first rendezvous and dock with a separate landing vehicle in lunar orbit. That vehicle, in turn, must be launched, refueled in space, and positioned with precise timing. Each of these steps represents a complex operation on its own. When combined, they form a chain where each link depends on the others functioning perfectly. One concern raised by safety reviewers was the number of first-time events being attempted simultaneously. The first crewed docking in this configuration, the first large-scale transfer of cryogenic fuel in space, the first operational use of entirely new surface system. Individually, each milestone is achievable. Together, they significantly increase overall risk. And so the strategy has shifted. Rather than attempting everything at once, the program is stepping back to isolate and test these elements closer to Earth. The upcoming mission will focus on validating docking procedures, life support performance, and communication systems in an environment where intervention is still possible if something goes wrong. It is a quieter approach, but a more controlled one. By keeping the mission within Earth's vicinity, the distance is reduced from hundreds of thousands of kilometers to something far more manageable. That difference may not sound dramatic, but in operational terms, it changes everything. Response times are shorter, support options are greater, and uncertainties become easier to contain. which raises an interesting perspective. If reaching the moon is no longer the immediate goal, then the question becomes not just when we will return, but how carefully we are willing to proceed before we do. This shift in mission planning does not stop at how the missions are flown. It extends deeper into the design of the rocket itself. For years, there had been a clear roadmap for upgrading the launch system. A more powerful configuration was planned, built around a new upper stage designed to significantly increase performance. In theory, it would allow heavier payloads, more ambitious missions, and greater flexibility in how those missions were executed. In practice, however, the development of this upgrade had become increasingly difficult. Delays accumulated, costs rose, and over time, the gap between what was planned and what was achievable began to widen. So a different decision was made. Rather than continuing down that path, the upgrade was set aside entirely. In its place, a more immediate and pragmatic solution was chosen: a different upper stage, already in operation on another launch system, would be adapted and integrated instead. This alternative is not entirely new. It is a dual-engine stage with a proven track record, capable of carrying a substantial amount of propellant. While not originally designed for this specific rocket, it can be incorporated with relatively minimal changes. And that detail is important, because one of the limiting factors in the current system is not just the rocket itself, but the infrastructure that supports it. By selecting a configuration that remains compatible with existing ground systems, the need for entirely new launch facilities is avoided, which, in turn, removes another source of delay. There is also a broader intention behind this decision. By simplifying and standardizing the architecture, the program aims to move away from long gaps between launches. Instead of waiting years between missions, the goal is to build toward a more consistent cadence, approaching one launch roughly every 10 months. It is a shift from ambition towards sustainability. But this leads to a more immediate question. If the third mission is no longer the moment of return, then when will that moment actually arrive? The current target points further ahead than many had expected. The next opportunity for a landing is now projected toward the latter part of the decade, and yet, the significance of that mission may justify the delay, because the destination itself is unlike anything explored before. Earlier missions focused on regions closer to the lunar equator, where conditions were relatively stable and predictable. This time, the focus has shifted toward the southern polar region, a place defined not by familiarity, but by extremes. Here, the sun sits low along the horizon, casting long, unmoving shadows across the surface. Some areas have remained in darkness for billions of years, untouched by direct sunlight. Temperatures in these regions can drop to levels colder than almost anywhere else in the solar system. It is a harsh environment, but it may also be one of the most valuable places we have ever attempted to reach, which raises a final thought. If returning to the moon is no longer just about going back, but about going somewhere entirely new, then perhaps the timeline is only part of the story. This region exists because of something subtle, yet profound. The moon's axis is tilted by only about 1.5 degrees. As a result, sunlight never rises high in the sky near the poles. It lingers low along the horizon, stretching shadows across the surface that, in some places, have not shifted for billions of years. These are known as permanently shadowed regions. Inside these craters, temperatures can fall to nearly -240 degrees Celsius. Conditions so cold that even worlds far beyond Earth can appear comparatively warm. At first glance, they seem like places of absolute desolation, but they may hold something unexpectedly valuable, because in these regions, something has been preserved over immense stretches of time. Water delivered by comets and asteroids is thought to have accumulated and remained frozen. Protected from sunlight within these shadowed basins, this is where the nature of the mission begins to change. What might once have been seen as a purely scientific endeavor is now also viewed through a different lens. If this ice can be accessed, it can be transformed, broken down into oxygen for breathing, and hydrogen for fuel. In that sense, the moon becomes more than a destination. It becomes a resource, a potential point of departure for missions that extend far beyond it. And this is why the next landing site matters so much. To explore this environment, a new generation of instruments will be carried to the surface. Among them is a system designed to study one of the most underestimated challenges of lunar exploration: dust. At a distance, lunar dust might seem insignificant, but up close, it behaves very differently from anything we encounter on Earth. Rather than smooth, rounded particles shaped by wind and water, it consists of sharp, irregular fragments formed through billions of years of impact. Even more problematic, these particles can become electrically charged under constant exposure to solar radiation. As a result, they cling to surfaces, infiltrate mechanisms, and gradually wear down materials over time. For astronauts, this is more than an inconvenience. It is a persistent hazard. To better understand it, a dedicated instrument will observe how this dust behaves in real conditions. Mounted on a small autonomous rover, it will monitor how particles move when a lander arrives, and how they respond to human activity on the surface. Because before we can live and work on the moon, we first need to understand the environment at its most unforgiving. Alongside these surface studies, another instrument will focus on something far less visible. Yet equally important, a seismic station will be deployed to listen, quite literally, to the internal activity of the moon. By measuring subtle vibrations caused by moonquakes and meteorite impacts, it can begin to reveal what lies beneath the surface. But the analysis does not stop there. Astronauts will also carry a device designed to generate controlled seismic pulses into the ground. By observing how these waves travel and reflect back, it becomes possible to map the hidden structure below their feet. Layers, fractures, and perhaps even deposits of buried ice can be inferred from these signals. In a place where direct observation is limited, this becomes a way of seeing the invisible. One location, in particular, has drawn significant attention: a crater near the lunar South Pole, spanning roughly 20 kilometers across and descending several kilometers deep. Its steep inner walls create conditions where sunlight never reaches the base, forming a natural trap for volatile materials that may have accumulated over immense periods of time. It is an environment as challenging as it is intriguing, and operating within it requires more than advanced instruments. It requires a new approach to human presence itself. The next generation of lunar explorers will rely on a redesigned suit built not just for survival, but for mobility and endurance in extreme conditions. Earlier suits, while effective, were rigid and restrictive. Movement was limited, forcing astronauts to adapt their behavior to the suit rather than the other way around. This time, that relationship is being rethought. The new design combines rigid structural elements with flexible joint systems, allowing for a range of motion that was previously difficult to achieve in a pressurized environment. Walking, bending, and working on the surface become more natural, more controlled. In many ways, the suit functions as a personal spacecraft. It carries its own life support system, capable of maintaining stable conditions even in the intense cold of permanently shadowed regions for extended periods. It integrates communication systems that maintain a continuous link with surrounding equipment and mission control. The visor itself is designed not only for protection, but for clarity and visibility under harsh lighting conditions. But perhaps most importantly, it is built with the lunar environment in mind. Every seal, every joint, every material is designed to resist the abrasive, persistent nature of lunar dust. Because on the moon, it is not just the large challenges that matter. It is the accumulation of small, relentless ones that ultimately determine whether we can stay. The upcoming mission will serve as the first true test of these suits in the vacuum of space. Not in simulations, not in controlled environments on Earth, but in the conditions they were designed for. Only after that will they be trusted for use on the lunar surface later in the decade. But beyond the engineering, beyond the science, there is another layer to this story that is more difficult to quantify. Because this is not just a return to the moon, it is also, in many ways, a race. Over recent years, another spacefaring nation has been steadily advancing its own lunar ambitions. Step by step, milestone by milestone. It has demonstrated increasing capability. Missions have returned samples from previously unexplored regions of the moon, and plans for a crewed landing within the next decade have already been outlined. This has introduced a new kind of urgency, not simply to explore, but to establish presence, particularly in regions believed to hold valuable resources, such as the lunar South Pole. The concern is not only about who arrives first, but about who is able to remain, to build infrastructure, and to define how that region is used in the future. If one nation were to secure a lasting foothold in such an area, it could shape the trajectory of exploration beyond the moon itself. And so, what began as a scientific initiative has gradually taken on a strategic dimension. The goals remain rooted in discovery, in understanding, in extending human presence beyond Earth, but they are now intertwined with broader considerations about access, influence, and long-term capability, which makes the outcome more uncertain. Because the journey to the moon has never been a straight path. It has always been shaped by iteration, by setback, and by the willingness to adapt, and perhaps that is still true today. In the late 1960s, reaching the moon required a willingness to accept extraordinary risks. It was a race defined by urgency, driven by competition, and measured in moments that would shape history. Today, the context has shifted. The objective is no longer simply to arrive, to leave a mark, and to return home. What matters now is what comes after: the ability to remain, to operate, to build something that extends beyond a single mission. Each adjustment we have explored reflects that shift: a more standardized launch system, missions designed to test and refine rather than rush ahead, a gradual layering of capability instead of a single defining leap. Together, they point toward a different kind of presence, one that is not temporary, but repeatable, because placing a human on the moon again, while significant, is only a beginning. It does not by itself establish continuity. It does not secure long-term access. Nor does it unlock the deeper potential of what the moon may offer. And that potential appears to be concentrated in one of the most extreme environments we have ever attempted to explore. At the lunar South Pole, in regions that have remained in darkness for billions of years, there is a record of the past preserved in ice, a resource that could support future exploration, and perhaps even enable it, not just for returning to the moon, but for traveling far beyond it. Reaching that point will take time. The timeline has stretched further than originally expected. The path has become more complex, shaped by technical challenges, careful reassessment, and a growing awareness of what is truly required to succeed. But perhaps that is not a setback. Perhaps it is a sign that the goal itself has evolved. Because what is being built now is not designed for a single decade. It is intended to endure for far longer. And so, as preparations continue and the next mission moves closer to launch, there is a quiet sense of anticipation, not just for a moment of arrival, but for what that moment represents. A return, certainly, but also the beginning of something that may extend well beyond it. And perhaps the most interesting question is not when we will step onto the moon again, but what we will choose to do once we are there. This video was created independently, with a focus on clarity, depth, and curiosity. If you find value in this kind of exploration, you can support the channel simply by subscribing. It helps more than it might seem. Each new subscriber allows these videos to reach further, to grow steadily, and to continue improving over time. And if you would like to go a step further, joining the community is a way to directly support the work behind the scenes. It helps keep the focus where it belongs, on making complex ideas more accessible, and on continuing to explore questions that don't always have simple answers. If this is the kind of content you want to see more of, you are always welcome here.